Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello, let us continue our discussion on mechanical testing. We are looking at tensile test and its results and interpretation, how to understand the material behavior with respect to tensile deformation. So far we have looked at the fundamentals of stress-strain relation, how it characterizes the material, and what are the various simple relations, how it connects to the work hardening behavior and other tensile properties. Now we look at the type of tensile behavior which which is exhibited by most of the class of materials. Okay, so the first one is linear elastic response, type 1. It is sometimes referred as type 1, which is a linear stress-strain relationship. For example, this is plaster of Paris, and this is cemented tungsten carbide. And there are two ways in which the elastic limit can be exceeded: immediate fracture or plastic deformation followed by fracture. See, if you recall the previous classes, we always looked at a stress-strain curve as an elastic portion, yield point, and then plastic portion. Right? So here, these kind of stress-strain curves do not have the neither yield point nor a plastic portion. Okay, so that means how do we understand this? This is a stress-strain behavior exhibited by a material, almost insignificant plastic deformation. It is highly brittle in nature. Okay, so the figure shows the stress-strain response of typical of ceramic, a silicate glass, or certain metals at low temperatures. Even a ductile material such as metals at very low temperature, they can have the potential to exhibit similar behavior. But in general, these kind of stress-strain relations are exhibited by the ceramic material, especially whatever the examples I have shown is a plaster of Paris is a kind of a ceramic, and then tungsten carbide is also a ceramic. So what it means is these systems show very limited plastic deformation or unnoticeable plastic deformation. Okay. On the other hand, you can also say that the fracture occurs without any noticeable plastic deformation or warning. See, the work hardening nature of the ductile materials also, it's a kind of a warning before fracture, right? So, but that kind of behavior is not seen or exhibited by these kind of highly brittle materials. Okay, so this is one type of stress-strain behavior. We understand this why ceramics exhibits this kind of behavior, because we know that the number of slip systems available for plastic deformation is very limited, at least at low temperature. But at high temperatures, obviously, there is a possibility of for this material to exhibit some plasticity. So that we will see as we go along with the high temperature deformation. Okay. See, as far as room temperature deformation is concerned, ceramic materials are they will exhibit highly brittle nature. So the next type of stress-strain curve or the stress-strain behavior is elastic homogeneous plastic response, that is type 2. So this is a typical stress-strain curve which is exhibited by most of the engineering materials, especially metal alloys and high temperature materials or any other material which exhibits similar kind of stress-strain behavior. Please note that this is a elastic portion, and then after that it is a continuous yielding to the maximum, and then it fails here, so it is a fracture stress. And then the yield point is always determined in any material which shows a continuous yielding behavior through this method that is called proof stress. This is called proof stress. How do we do this proof stress measurement? We just mark a point at 0.002 strain and then draw a parallel line wherever it intersects in the stress strain curve. That point is considered as yield stress, or normally it is called 0.2% proof stress. Okay, so that is how it is known. So what I'm trying to show in this very important aspect, this we have already seen in the beginning of this chapter. What is that we are trying to explain here? This plot is elongation versus gauge length, and what you are seeing here, A, B, C, D, E marked here is also marked here. So what is this? Let us look at the descriptors. Total strain values will be higher for shorter gauge length. Hence, both specimen size and total strain to be reported. This aspect we have seen. But what you have to see here is, because of the necking, how the gauge length influences the percentage elongation is clearly reported here. Okay. You can, for example, you look at this point D here, which is just after the maximum load. That means after the necking, you can see the influence of the gauge length. Okay, from here to here, the maximum gauge length can be up to this point. So, which is not a true representation of uniform elongation. Okay, it is influenced highly by necking. Okay, and that is how it is shown. So before fracture, close to fracture, it influences significantly. The elongation influences significantly. So the engineering stress strain curve, points A, B, C, D, and E are arbitrary stress levels shown in B. A schematic representation of specimen elongation along the gauge line. Uniform extension occurs up to the onset of necking. Additional displacements are localized in the neck region D and E. So these are the additional displacements because of the necking. So let us talk about the strain distribution. The total strain reported for a given test result will depend on the gauge length of the test bar. It is clear that as the gauge length decreases, the elongation involved in the necking process becomes increasingly more dominant. Consequently, total strain values after necking commences will be larger for bars with gauge length, shorter gauge length, and for which the length of the neck region is larger fraction of the total length. So this particular contribution, either D or E, that is larger fraction of the total length. That is what it is mentioned. So this type of stress strain behavior is elastic and then homogeneous plastic response by the material. And the next one is elastic heterogeneous plastic response, which is something like this. So if you have a stress strain behavior by material, something like this, we need to know why it is so. Why it is so? When hexagonal close packed metals are tested over a relatively wide temperature range, they tend to deform plastically by a combination of slip along glide planes and twinning in the discrete zones within the specimen. We know that in HCP system, unlike FCC, they have limited slip systems. Okay, so the deformation mode there, it is a combination of slip and twinning. Okay, that's what it is. When twinning occurs, extension of the gauge length proceeds in discrete bursts that are associated with twin band nucleation and growth. Very important point. You see, as the extension of the gauge length proceeds, that means as you pull the specimen in a tensile direction, discrete bursts that are associated with the twin twin band nucleation and growth. So twin band, when the twin band nucleates, there is a burst. So that is what it's shown here, and that causes this kind of serration. Often these bursts of deformation are associated with audible click emitted from within the sample. People have recorded this audio in most of the experiments just for observation. Whenever the instantaneous strain rate in the specimen exceeds the rate of motion of the test machine crosshead, a load drop will occur. So this is a well-known fact that the instantaneous rate in the specimen, wherever it exceeds the rate of motion of the test machine crosshead, a load drop will take place. A similar stress strain response is found in BCC metals tested at low temperatures and in FCC metals tested under a combination of low temperature and high strain rates. So what we have to appreciate here is whenever you have a constrained deformation, either in the form of low temperature, high strain rate, or the lack of slip systems, something like that. So we have, wherever you have a constrained plastic deformation, so this kind of phenomena can occur. So the next type is elastic, heterogeneous plastic, homogeneous plastic. So what is that? This is also well known, but it has been classified like this. So you have elastic behavior, and immediately there is a heterogeneous plastic and then homogeneous plastic. So this is a very well known and a classical stress strain behavior, which is being taught and it's reported in most of the elementary textbooks. So let us see what it is. So after being loaded elastically to A, defined as an upper yield point, the material is observed to develop a local deformation band. So this is called yield point phenomenon. Okay, this kind of the material reaches a point up to A, and then suddenly the load, the stress drops or load drop, and then it develop a local deformation band. So it is a local deformation band. So it is called upper yield point, and this is a lower yield point, this level. The sudden onset of plastic deformation associated with this Luder band is responsible for the initial load drop to be defined as lower yield point. So what is the reason for this kind of a sudden load drop from point A to point B? People have studied that this is because of something called Luder's band. Okay, so we just mentioned in the previous sentence it is local deformation, so it is characterized as a Luder band. We will see what it is in a minute. Outside the Luder band, the material still loaded elastically. Okay, so outside this is still elastic stress is associated with the specimen. Yeah. The remainder of the heterogeneous segment of the deformation B to C is consumed in the passage of Luder band across the entire gauge section. So it is not just the Luder band is responsible for this load drop or the formation of the load drop. We are saying that it associated with the formation of the Luder band. It is not just that. It has to propagate throughout the gauge of the specimen up to C. Okay. When the deformation has spread to all the parts of the gauge length, the material then continues to deform in a homogeneous manner with work hardening, necking, and eventual failure. So after this, a complete spread of Luder band throughout the gauge length, the material tried to deform homogeneously, then it exhibits strain hardening, reaches a maximum, and then necking, and then fracture. So the rest of the other behavior we know. So we are trying to study this yield point phenomenon now. This localized plastic deformation phenomenon is known as, or is well known for low carbon steels, in which the interstitial carbon and nitrogen atoms can form atmospheres around the dislocations. You see, now we have to go back to our dislocation lectures and then try to recall some of the mechanics of dislocation and how the interstitial atom interacts with the dislocation. So we have seen a couple of examples, especially interstitial atom like carbon, how it goes and interacts with the edge dislocation. We have seen that, right? So recall those lectures, and then so when the interstitial atom interacts with the edge dislocation, it forms an atmosphere, which also will reduce the energy of the dislocation. This also we have seen, right? How the elemental segregation around the dislocation, how it reduces energy. Okay, so that scenario is here described here as atmospheres, right, around dislocation. These atmospheres strongly pin the dislocation, making it difficult to move them initially. That is, we are trying to explain at the point A. Okay, the stress keep on increasing, and then at the point it just locked up. So at the point A, the dislocation and interstitial interaction is pretty strong, and the dislocation motion is restricted at the point A. However, once the dislocations break away from the pinning solute atoms and become mobile, it is relatively easy to continue their movement. So there is something called unpinning force here after the point A. The dislocation has to unpin from the interstitial atoms and then try to move. Okay, we will continue that discussion. Here is same stress strain diagram in a much more elaborate manner. Here the point of interest here is, I just want to show from the B to C in the previous plot. It has got some elaborate description here. After the lower yield point, then the complete the band is called yield point elongation. How this Luder band propagates from the point B to point C, which is nicely shown in this schematic. So what you are seeing here is the Luder band nucleates from the point B of the initial, previous plot, and then you can see that Luder band occupies, and then this middle portion is unyielded metal. So as the deformation proceeds, then the region occupied by the Luder band is keep on increasing, and finally it is going to fill the gauge line. So this is called Luder band. Okay. The extent of elongation associated with the discontinuous yielding process is called yield point elongation, or the Luder strain. Luder strain. So this complete strain is the Luder strain, and it is identified as the change in elongation between upper and lower yield points. A good surface finish requires that the yield point elongation be minimized or avoided by appropriate alloy design. You see, this kind of local deformation yielding is not preferred in the application point of view. Okay, but scientifically it is very interesting to note all this, but from an application point of view, these are all not preferred. So a good surface finish or even an alloy design. Alloy design means what? There are alloying elements which can combine these interstitial elements into form a stable carbide and nitrides. So it's a kind of fixing this interstitial atom. That is called alloy design, right? By proper alloy design, we can remove this elemental carbon and elemental nitrogen and so on, right? Like titanium. Okay, normally it is added to fix the oxygen there, right? It will form titanium dioxide and carbon, nitrogen. All these interstitial elements can be fixed in the form of or by formation of carbides and nitrides and oxides. These things can be fixed by alloy design. As long as they are not there in the free form, you don't have to worry about this yield point phenomenon. Plastic deformation beyond the yield point elongation stage also eliminates subsequent Loader band formation. Although with a mild heat treatment, it is possible for the solute atoms to reform pinning atmospheres. So you may do the plastic deformation to fix this, but then little bit of heat treatment again will promote the diffusion of this interstitial, and then again it will form the pinning atmospheres, or it will interact with the dislocations. So this strain aging treatment restores the upper yield point behavior. This is, the interstitial coming out of this pinning and then it relaxing and get back to again pinning is called strain aging. We will see that this aspect separately in few minutes. Carbon and nitrogen atoms possess a strong attraction for both edge and screw dislocations within the BCC ion lattice. Accordingly, a solute atmosphere is formed around each dislocation core. Since these dislocations are pinned by such solute atmospheres, dislocation motion is severely restricted until a sufficiently high stress, that is the upper yield point on curve A, is applied to enable the dislocation to rip free and move through the lattice. According to the theory, these unpinned dislocations multiply rapidly by multiple cross-slip mechanism. As a result, the number of mobile dislocation increases sharply, yielding becomes easier, and the load necessary for continued deformation decreases to the level associated with the lower yield point. Okay, marked as a point A on curve A. So here we are talking about this. So now, having understood this yield point phenomenon, we will now discuss something called strain aging aspect in the context of yield point phenomenon. Look at this schematic stress strain diagram. In fact, we have just combined all the type of stress strain diagram in one plot and then try to address this. The curve A is yield point behavior, curve B is ordinary homogeneous. This is curve B. It goes like this. Homogeneous yield and strain hardening response after reloading. Curve C is a serrated yield behavior associated with the dislocation solute atom interactions leading to heterogeneous plastic deformation. Curve D, ordinary strain hardening behavior associated with homogeneous plastic deformation. As additional regions, that is the Loader bands, apart from this, the additional regions deform in this manner, the stress level remains relatively constant until essentially all the dislocation have broken free from the respective solute atom clusters. At this point, continued deformation takes place by homogeneous plastic flow, curve A beginning at the point B. So it is a similar description, what I have just said in the previous slide. It is a repetition here. It's a kind of redundant information. Just to give the combined description, I brought them again. Okay. So furthermore, if the test was interrupted, suppose after this Loader band region, the material start to deform homogeneously, you stop in between and then unload them or interrupt them. That is what it is written here. The test was interrupted after completion of Loader strain region AB, and the load removed and then immediately reapplied, the subsequent stress strain curve would not display any yield point. This we have already discussed in the previous slide, but just here it is shown as a schematic. So just after the yield point elongation, if you just unload and then quickly reload them, then this band will not reappear. But if you heat them, it will reappear. That's the point you have to remember. Okay. So yield point phenomenon does not explain similar yield point behavior in other materials such as silicon, germanium, and lithium fluoride. Okay. So the yield point phenomenon is quite popular in the context of mild steels, right? So steel being a very important material, this was quite a popular theory, and it was giving a nice explanation. The interstitial atoms interaction with the dislocation causes this yield point phenomenon. But that doesn't explain a similar, yield point behavior such as silicon, germanium, and lithium fluoride. So what is the reason? Johnston and Horn have proposed that yield point behavior in these crystals is related to an initially low mobile dislocation density and a low dislocation velocity stress sensitivity. It is a bit complicated description, but it's still interesting point to note. We are bringing two parameters to explain the yield point phenomenon other than the low carbon steel. That is low mobile dislocation density. It is not just dislocation density, it's a mobile dislocation density, right? The low mobile dislocation density and a low dislocation velocity stress sensitivity. Dislocation velocity. We have seen this before. We related this dislocation velocity to dislocation density earlier. Okay, so we will look at them again. Regarding the later, studies by Gilman and Johnston and others demonstrated that the dislocation velocity V depends on the resolved shear stress as given by V is equal to tau by D to the power M. Okay, where V is the dislocation velocity, tau is applied resolved shear stress, D and M are material properties. Defining the plastic strain rate, epsilon P dot is proportional to NBV. What is this? Where epsilon P dot is a plastic strain rate, N is the number of dislocations per unit area free to move about and multiply. V is Berger's vector, P is a dislocation velocity. So these researchers have looked at the parameters involving these terms. So here it is not just number of dislocations. Here it is number of dislocation per unit area which are free to move and about and multiply. So this is a very specific characteristic of a dislocation. So they are looking at a specific form of a dislocation which can explain this yield point phenomenon in this materials like silicon and germanium. Johnston argued that when the initial mobile dislocation density is low, the plastic strain rate would be less than the rate of movement of the test machine crosshead, and little over plastic deformation would be detected. Okay. Now, at higher stress levels, the dislocations would be moving at a higher velocity and also begin to multiply rapidly, such that the total plastic strain rate would then exceed the rate of crosshead movement. So we are now comparing two things. What are two things? The plastic strain rate, which is experienced by the material. Other one is the movement of the test machine, that is a crosshead speed. We are comparing these two. Okay. To balance the two rates, the dislocation velocity would have to decrease. To keep the deformation going in a manner, something has to compensate. So these two rates have to come into an equilibrium or a balance. So for that, the dislocation velocity would have to decrease. So if m is very small, that exponent what we have seen in the previous slide, which is less than 20, which is typical of ionic and covalent solids, then the large drop in the load would be required to reduce the dislocation velocity by the necessary amount. If m is large, which is or greater than 100 to 200, which is typical of FCC type of metals and materials, only a small load drop would be required to effect a substantial change in dislocation velocity. Okay. So depending upon the initial mobile dislocation density and the stress state sensitivity, this can be explained. That is what these researchers have demonstrated. That means for a small m value, a large load drop will be there in the material. Something. These studies have been reported already. You can look at the references what I have given for the further details. Okay, I just want to bring the context of yield point phenomenon. You should not think that this is all applied only to steels and low carbon steels. It is there in all the other materials, but then people have given a different type of interpretation and explanation, which is quite interesting as well. So for the large m values, the load drop will be much small. That will compensate the dislocation velocity.